Okay, hello class. This is our weekly update, and a little bit late. I've been waiting for some sunshine, but the last couple days we haven't had any. So I'll be doing a lot of just verbal talking here, but then I'll just do a little bit on the whiteboard, and I'll try to write a little bigger this time with the update. So a lot of announcements. First, thank you. Several people, a few folks, Joe, Rian, and Lane emailed me about Oaks things, so I was able to, I think I had some due dates wrong, had a couple little details, so I appreciate that. Whenever you notice that, let me know and I'll update it for the class. Also, thank you to Jenna and Haley, H-A, we have a couple Haleys, this one's H-A-I-L, Haley. Noticed a problem with one of the, it was the do the calculation where you had to do contour maps, and there was a function like this. Z is 2 minus x cubed or something like that. And a couple of you noticed that, hey, there is actually a free variable. Y is free, and a couple people, I think Haley might have been one as well, were like, hey, it's free, or Ellie maybe even exclamation, like that makes it easier, even though it was on the contour map page. And so you can do it using the techniques from earlier. And in future editions, I'll put that Y in there. So thank you guys for noticing that. So bonus for Jenna and Haley on that email. Next thing, also thank you to Rian and Haley for a suggestion about the quizzes. I didn't realize that on Oaks, you don't see graded, but you don't see which problems are correct. Again, you get multiple chances on the quizzes. This is about learning. I want you to use the quiz as a learning opportunity. Make sure you understand these concepts. It's a way to give yourself feedback about how you're doing with the class. And so what I'm going to change them to, I'm hoping this module, that quiz 4 and 5 should be this way, but let me know if they're not, where you should see which ones you've gotten correct. And so the next time you go through to redo it, you can focus on, say, these 3. Oh, and advice for, so some people are a little concerned, like they want to do better on the quizzes, and I guess advice to prepare for those, if you like, is I'm taking these questions mostly directly from the journal, maybe a little bit of modification, but at the end of every chapter in your journal, there's a concept review section. And so often I'm taking those questions there, and then I might take a few from the calculation as well. So if you want to practice up and you can review on those, there's answers for at the end of the chapter on the concept and calculation review. Okay, third thing, the assignment, the discussion assignment, a derivative is, so great job on those. I think a couple of my particular favorites were Haley, H-A-L-L-E, that Haley, and Dallas have just a really nice, simple, hey, derivative is a rate of change. And so a short, succinct one. I also like Jeff's discussion about how derivatives often help you in unrelated ways. Like his example was L'Hopital's rule. A couple of you commented, I agree, I like that. And then Jenna actually gave you a preview to this module in chapter 2. You're learning about partial derivatives, and she gave an example. So she plays soccer. She's on the soccer team. She's constantly worrying about how to optimize her skill level. And so I think she was saying something like this, like maybe her skill is a function of several things. Maybe X is like her endurance, Y is her speed, and Z is like her footwork. And she, oh sorry, so we need another one, W here. And so it was great, it was an excellent example that was a preview for what we're gonna do in this chapter, which is we're gonna be able to measure is, if she were to increase her endurance by a little bit, how much does that actually affect her overall skill as a soccer player? Versus maybe spending more time on her footwork, maybe putting a bit more time there has more of a payoff in her overall skills as an athlete. So great example, thank you for that, Jenna. Okay, next assignment. Oh, I thought it was, you guys did a great job on the topo map ones and the contour maps, visualizing those. And I'm going to post some of the good examples in the samples and examples section. But it delighted me to think about many of you, if you were working on campus back on the bricks and you saw someone with their hand like all blue or pink or whatever red from their contour map, like, oh yeah, you're in 221. really nice job on that assignment. Then the bottle traces, overall, awesome job on those. Do have some favorites, and again, I'm going to post those. So Brooke made a comment that made me think this might be a good idea. And so unless you contact me and say you don't want me to do this, I'm assuming as if we were in class, like if I saw a really good example, I'm like, hey, this is Dallas's example. I just want to show you what he did here. So I'm going to post some of the ones that I liked and I thought were particularly good explanations each week. So if you had trouble, so we're now in chapter 2, but if you're like, hey, I really would like to review a couple things from chapter 1. I wasn't so sure about certain things and I want to go back and take a look. So I'm going to post some of the excellent assignments from chapter 1 at the beginning of chapter 2, and it'll say like optional review. So if you want to take a look at those, you can look through your classmates' work, and some in particular that are really good. Just in general, I've found Emma's been shooting a lot of videos with excellent explanations of why she's doing what she's doing each time. So check hers out. Eddie's also done a really nice job. He did the bottle traces one with a light bulb, which he turned upside down, and really nice discussion there. Lily and Ellie often turn in PDF files that are very clear, step-by-step what they're doing. So again, I'm going to put a bunch in there. Check if yours is in there. Again, kudos to all the folks that did that. And check them out if you need more review, or it's a good person to say, hey, I really do seem to understand every time Eddie's talking. So shoot him an email and be like, hey, I want to work together on the homework this week. Let's FaceTime, or let's just chat back and forth with email. Okay, so then that was, all those projects. Oh yeah, so that's a good way to get your study buddy, and you should be able to find people's contact information. That was the point of that module 0 or orientation discussion board, where you had to meet your classmates and write your names and contact information. So don't be shy about doing that, particularly this semester. It's important that I want us all learning together. I don't want anyone getting left behind. And at this point, from seeing how you guys did in chapter 1 and on the challenge problem, I feel like we're doing good. Like we're almost all there together. Maybe a few people that would like to get a little bit higher, and we can help them out. Okay, so then I'll quickly talk about challenge 1. Every group did that particular challenge, so nobody chose for the vector. But the plus side of that is we need that contour stuff, and it really seemed to me that solidified a lot of the ideas for you guys. Many of the groups did multiple level ups, which is really neat to see. Just a fantastic job. I feel like as a class, we seem to thoroughly understand contour maps. The other good thing is that challenge 2 is about vectors, and book 3.5, which is again super cool. It's really visual again. We're going to be looking at curves through space. So we'll come back to vectors, and we're going to do quite a bit. The title of that book is Vector Calculus. So we will come back to those. We won't. We'll get a chance to make sure we thoroughly understand vectors. So I feel good that even though no group did that, we'll get to that topic eventually. A couple folks asked me, Charles, I think this was Charles and Lainey. Again, we got 2 lanes of Lainey with an IE. Commented that it was a little confusing, and I do apologize for this as well, that in the instructions for the challenge problems, it said something about critiquing, doing a peer review of other groups. We're not going to do that till later in the semester. So if it says that in the future, ignore it until I, let you know. So it might be that in the future, I might say, hey, particular groups do number 5, and particular groups do number 6, and then we'll swap, and you'll peer review. If you did 5, you'll get to peer review 6, so you'll get the access to that information and sort of learn through your classmates. Okay, so then a few things. I do want to do a few comments on the challenge problems, just to in general talk about some of the ones I really liked, which was so many of them, and different for different facets. So group 2, I don't know the team name, so I apologize for that. Maybe you can put them on the top now. But this was Lily, Ethan, and Dallas. Really nice summary, beautiful images in there, and excellent text that went with it. Group 7, which was Lane, Sam, and Jenna. This was the group that was closest out of all the groups in their explanation, saying like, you knew what z equals x squared plus y squared does, right? At this point, we're pretty familiar with that. Circular paraboloid opening up from the origin. And then when you just stick an ln, what does that do? And think about the shape of the LN graph. It's like this. And now it's going to take that and go in 3 dimensions. And so, that's why you get this shape that looks like the penny race at the mall, or which group was it? I really liked this one group showed a picture of a black hole singularity, and that's cool because we have so many physics, astrophysics, astronomy majors. Which one was that? Oh yeah, that was Eddie, Cameron, Kyra, and Michael. Really nice group overall. The way you use color throughout your thing, encoded the thing, the graphic design was nice, the images, and but it was group 7, Lane, Sam, and Jenna that like got closest at hinting at by just applying this operator. You go from this and you sort of see that LN shape here. Oh, I need a better marker, don't I? No, it's dying. A little bit better. Okay. And let's see. Oh, group 10, Jeff, Nate, and Haley, H-A-L-E. Really nice explanation too of your group's contributions, what each of you do. It really did seem like you interacted well as a group and got this project done. Let's see. Group 13, I just want to comment, was short, very succinct and accurate. Like you don't need to go into great detail if you got it down, and I think that was an excellent explanation of that. Group 8, Joe, Brianna, I think we have two of those. This is Brianna with an E, so B-R-E-A-N-N-A, and Filippo. Really nice graphic design where they had their figures labeled with captions. That's super helpful. But they did 3 level ups. That's bonus. Nice job. And group 9, Lainey, I-E, Brianna with an I, and Lee. Again, beautiful captions, beautiful picture of their sculpture at the end. And they did every single level up. So all levels up 2 through 6. And I just wanted to show you which group number you guys. I like their sculpture that they chose at the end, group 9. So let me do a quick screen share. And again, I think this is group 9. So they got that. Yeah, Lainey, Brianna, and Lee. There you are. Again, really nice color coding of what each team member did, contribution section, and here we go to the report. Okay, so nice captions and figures. Again, that's just a good practice to do in general. Really nice picture, hand drawn, looks good. And then, oh yeah, here we go, all the levels up. And just keep on going with these really nice hand drawn, showing the level curve step by step, what each case in level 5, a couple groups did level 5. That was nice to see. And then level 6, they did a transformation. So they put some weights in front of this, so made it elliptic probably, then the sign. So think about what would the sign do? Well, the sign has these undulations, and really cool. So I think that would be, if I walked into Museum of Math and the foyer there and saw that, that's awesome. By the way, there is a Museum of Math in New York City, so just opened maybe 3 or 4 years ago. It's a really cool place. If you're ever up that way, check it out. Okay. Last comment. Okay, so surveys. So a few of you, maybe 8 or 10 of you did the survey. Thank you. I really appreciate that. And a couple good questions came out of that. And also a few comments with thank you, Jenna. We've got more bonus. So that was a great, good eye on picking up that design error. I shouldn't have you fold something that you need the page behind it or cut it out. And then Sam, you should be a science editor. Yours are incredible, super helpful. I think I got 6 bonus points for you just by all those typos and grammar errors and just phrasing, and so I appreciate that. And let's see, then Lucas had a good comment and question, and Nia, I think, might mention domain and range again. So I think those questions helped you if you watch the office hours to do challenge 1, because it seemed like every group now understands domain and range. But Lucas had one more question. So last thing I want to do today. Lucas had a question. He's like, how can I tell from the vectors just by looking at their, how can I tell from planes representation by looking at their vectors? So let's say I have a plane, let's say z equals 4, x equals 2, and x plus y plus z equals 3. And he's like, how can I tell just kind of looking at the representation here, which ones are parallel and which ones are perpendicular. And there actually is a nice way to do this, easy way to do it, and we're going to need this more often throughout book 3, but also in book 3.5. So clearly they're all planes, linear in all the variables. Z equals 4, hopefully right now, that's horizontal. That's where you're ready to immediately say that. X equals 2, you know that's a vertical plane. Okay, well you know by thinking of them that way that they're perpendicular. But his question was, how can I tell from like the vector representations? Remember, each plane has a normal vector, which is you pull off the coefficients when it's in this form: ax plus by plus cz equals d. Once you've written it with all the letters on one side and the constant on the other, you pull off the coefficients. And so in this case, in the normal vector, we usually call it n, and that's a, b, and c. And so the vector for this one would be 0, 0, 1. The vector for this one would be 1, 0, 0. And the vector for the last one would be 1, 1, 1. Okay, once you've pulled those off, again, back to Lucas's question, how can I just look at those and say, oh, I know that this pair is perpendicular, this pair is parallel, this pair is neither. Okay, well the first ones, if I need them to be parallel, perpendicular, or neither, I'm really just asking a question about the angle between these planes. Do they intersect? And then what's the angle between them? And that's all answered with the formula, which is the dot product. Let's call this N1, N2, and N3. So N1 dotted with N2. That's going to give us information that we need to get the angle in the angle formula. We didn't do a whole lot with the dot product. Don't worry, we're going to do a lot of that in book 3.5, chapter 1. But for now, all you need to know is the dot product. If you're in 203 linear algebra, you probably got this down already. But you take the first components and multiply them, plus second components and multiply them, plus the third components and multiply them. Okay, so 0 times 1 is 0, 0, 0. So the dot product between these two vectors is 0. And when the dot product between two vectors is 0, that means the angle between them is 90. So go back to the formula in the beginning of chapter 1 about the angle between two vectors. If the angle between two vectors is 0, they're automatically perpendicular. So we know that these two are perpendicular, which we already knew visually by checking that. But let's say we want to try N2 and N3. Are those two perpendicular? The only way they're going to be perpendicular is if they have a dot product of 0. Well, this first one's already non-zero, so we're out. So you're just looking for like complementary zeros and complementary locations. So it can have like a 0, non-zero, 0, non-zero, right? But it doesn't happen here because 1 plus 1, 0, 0. So still 1, that's non-zero. So these are not perpendicular. These two do intersect. Oh, I didn't give you enough to say that. We know that those two are parallel, are not parallel, because the only way two planes are parallel is if their normal vectors are actually pointing in the same direction, which would mean one is a scalar multiple of the other. Is there any way I can multiply this vector N2 by some scalar and get that one? No, it's impossible because I've got these zeros here. So two vectors that are, maybe it would make more sense if I just give you a couple vectors that are parallel, like N4 is the vector 1, 2, 3, and 5 is the vector 3, 6, 9. Right. These would be the vectors describing two planes, x plus 2y plus 3z equals some number, and 3x plus 6y plus 9z equals some other number. Right? So these two planes have to be parallel because their normal vectors are pointing in the same direction. And you could divide this one by 3, right? And see that I'm x plus 2y plus 3z equals 5. Now look at those two. Now it's easy to see they're clearly pointing in the same direction. It's clearly that they are have the same normal vector, but that one is like above the other, right? Because of the 5 versus the 11. So there may be tilted planes. One's here and one's here, right? Okay, I think that's it. So great job this week. I hope you enjoy the partial derivatives. We're finally going to be like crank away and getting some applications with all the stuff that you've visualized now. All right, have fun.